everyone, welcome to BCP Med. In this video, we're going to be taking a look at formal charges, how they are calculated, some examples, how they are present in resonance structures, as well as how we can minimize formal charges and where they should go on atoms so as to best stabilize the molecule. Let's go ahead and get started. The first thing we want to go ahead and do is define what exactly a formal charge is. So a formal charge is going to describe the electron distribution on atoms within a molecule. It is a comparison, essentially, of the electron density in a given Lewis structure that we've drawn to the unbonded atom in free space. So what that means mathematically is that the formal charge is equal to the base number of valence electrons minus the number of electrons ascribed to it in the Lewis structure. And the number of electrons ascribed to it in the Lewis structure is the number of bonds plus the number of unbonded electrons. So we assume that each bond contributes one electron to that structure, not two because it's shared, so we say that it gets half a bond, plus the number of unbonded electrons, since those are all localized on that atom. So the formal charge is the base number of valence electrons minus the number of bonds plus unbonded electrons. So let's just do an example because that's the best way that we can visualize this. Let's look at the molecule N2O and ascribe some formal charges to each of the atoms. So if we start with the central atom, the nitrogen, we would see that it has a plus charge. Why is that the case? Well, it turns out that nitrogen normally has 5 valence electrons. In this case, the central nitrogen has 4 bonds and 0 unpaired electrons. So that would be 5 base valence electrons minus 4 from the bonds to give us a +1 overall formal charge. What about the oxygen on the right? Well, we see that this oxygen has 1 bond and 6 unpaired electrons. Oxygen normally has 6 valence electrons. So we would have 6 as the base valence minus 6 plus 1 for the unbonded plus bond. So that would be 6 minus 7 to give us a -1 formal charge overall, which would be indicated as a minus dash on the structure. The nitrogen on the left, though, has 2 unbonded electrons and 3 bonds to give us 5 electrons total on the Lewis structure, whereas nitrogen normally has 5 electrons. So it has a 0 formal charge in this structure, which we normally don't write anything when an atom has a 0 formal charge in a structure. Let's go ahead and look at another example. The ozone molecule, or O3. In this case, one of the oxygens has 3 bonds. So that 3-bonded oxygen is going to have 5 electrons ascribed to it in the structure, 2 unpaired and 3 from the bonds, whereas oxygen normally has 6 electrons. So that's going to be 6 minus 5, which is going to give a +1 overall charge to that oxygen. However, the single bonded oxygen in this case is going to have 7 electrons ascribed to it in the Lewis structure because it has 6 unbonded and 1 bond, whereas oxygen normally has 6 valence electrons. So in this case, we're going to have 6 minus 7, which is going to give us a -1 charge to that oxygen. You will eventually notice some patterns here such that all single bonded oxygens are going to be -1 charged, whereas all double bonded oxygens are always 0 charged. Same goes for nitrogen. Nitrogens that have triple bonds are going to have 0 formal charge, whereas nitrogens that carry double bonds will tend to have minus charges. So another structure that we can look at is carbon monoxide, which is a little bit tricky. So CO, the carbon is going to have 5 valence electrons ascribed to it in the Lewis structure, 3 bonds, 2 unbonded electrons, and that is going to give it a minus formal charge. The oxygen, on the other hand, is going to have 5 as well, because of the 3 bonds and 2 unbonded electrons, whereas oxygen normally has 6. And so 6 minus 5 will give us a plus formal charge on that oxygen. So that would be the formal charges for the carbon monoxide structure. Now, how do formal charges relate to polyatomic ions? Well, it turns out that the overall charge of a polyatomic ion is just the sum of the formal charges on the individual atoms. In fact, the formal charges on the atoms in a molecule must always add to the net charge of the molecule. Charge must be conserved. For example, let's look at the molecule NO2, nitrogen dioxide. It has a Lewis structure shown below. If we were to go ahead and ascribe formal charges, we would assign a minus charge to the oxygen on the left, since it's single bonded, and then we would assign a plus charge to the nitrogen in the middle, because in this Lewis structure, it has 4 electrons. The unbonded electron plus 3 bonds to give us 4, whereas nitrogen normally has 5, so that would be 5 minus 4 to give us plus 1. Notice that in this case, the plus and the minus add to a net 0 charge on the molecule. On the other hand, if you look at NO2-, the nitrite ion, you would see a Lewis structure that looks like this, where the formal charges, if you were to assign them, you would see a minus charge on the oxygen, same as before. However, now the nitrogen has a 0 formal charge because it has 5 electrons in the Lewis structure, and nitrogen normally has 5 valence electrons. So 5 minus 5 gives us 0, and 0 net charge. Notice the minus 1 charge on the oxygen is the same as the overall minus 1 charge of the ion. Conversely, if you look at the sulfate ion, SO4 2-, we would see the Lewis structure for that would be represented as such as the structure below, where you have the 2 minus 1 oxygens that are single bonded carry the appropriate formal charge, -1, whereas the double bonded oxygens are at 0 formal charge, since oxygen is normally at 6, and the double bonds in combination with the lone pairs give you 6 electrons in this Lewis structure. Sulfur likewise normally has 6, and the 6 bonds give it an overall 0 formal charge. The 2 -1 oxygens add up to a -2 overall formal charge, as indicated by the -2 on the sulfate ion. Now, how do resonance structures and formal charges work together? Well, resonance structures are multiple Lewis structures that can correctly describe the same molecule, right? So in reality, the molecule is a superposition of all the different resonance structures, and we go in depth into how that works in a different video dedicated to resonance structures. But what happens is that the change in the pi bond placement between different atoms, right, the different combinations of pi bonds, sometimes involve a shift in formal charge, as we can completely delocalize the pi electron density on one atom or another. So for example, if we look at the molecule N2O, we can see that one resonance structure has the formal charges in this configuration where N is plus and O is minus. However, it would be just as appropriate, or perhaps not just as appropriate, but it would also be appropriate to draw this resonance structure on the right, where we have 2 double bonds where the nitrogen in the middle still has a positive charge, but we have a negative charge on the nitrogen on the left instead of the oxygen. In reality, these combine to give the superposition shown here, where we have partial bonds to both the N and the O. But these two formally charged structures, we see that the formal charges flip-flop between resonance structures, and that is going to lead to certain preferences for one resonance structure over the other. So it is the case that formal charges actually have a preference on which atom they reside. When possible, we want to put formal charges on the atoms that best stabilize the given positive or negative charge. For negative charges, for example, this means the more polarizable and electronegative atom. So, for example, given the choice between oxygen and nitrogen, we would want to put the negative charge on the oxygen because O is substantially more electronegative than nitrogen, and so it better accommodates that minus charge. The nucleus is more comfortable holding in that extra electron density due to the higher effective nuclear charge. On the other hand, iodine better accommodates a negative charge than fluorine, because although fluorine is more electronegative, iodine is so big, the excess electron density can very nicely space itself out and minimize repulsions. So there's a combination between those two factors. In general, the resonance structure with better charge placement is going to contribute more to the overall superposition of the molecule. Right? The superposition is not an even distribution, it is skewed towards the preferred resonance structure. So for example, if we look at the N2O molecule, those two resonance structures, one of them is going to contribute more significantly. Which one is it going to be? Well, as we just noted, O carries a negative charge better than N, so between the two of these, the one on the left is going to be the preferred structure, and so it will contribute more to the overall structure of the molecule. Let's look at another example. The SCN ion is going to have an overall minus charge, or it can either be placed on the sulfur or on the nitrogen. In this case, nitrogen is more electronegative than sulfur. However, sulfur is far more polarizable than nitrogen. It turns out that the polarizability matters more, and sulfur better accommodates negative charges than does nitrogen. So once again, the structure on the left is going to be preferred, and so it will contribute more towards the overall structure of the molecule. Another thing that we want to consider is that formal charges are, in and of themselves, a little bit unstable. When we have multiple formal charges within a molecule, there is going to be an electrostatic attraction between them, which is going to put tension on the molecule as a whole. So sometimes, when you want to evaluate the reasonableness of a Lewis structure, we want to consider that formal charges that are closer to zero are better when it's possible. And if not zero, we want to minimize the overall magnitude of those formal charges. So for example, if we go back to the example that we've been working with, the N2L molecule, we can see that one structure is going to have the formal charges of plus and on the N and minus on the O, but we could also imagine a different Lewis structure, which would be valid via the octet rule, in which we have oxygen as the central atom with a +2 formal charge in the O and a -2 formal charge in the N. Although this follows the octet rule, these formal charges are not very good. They are not very close to zero, and there's a lot of electrostatic tension on this molecule. And because these atoms are period 2, they cannot go hypervalent and combine to get rid of those formal charges, and so we're stuck here with a lot of this electrostatic tension, and so this is going to be a bad Lewis structure. We don't like the structure, we much prefer the one on the left. It is a much better representation of the molecule. So another example, going back to the SCN ion, we might be asked to evaluate which is a better Lewis structure, the carbon being the central atom or the sulfur being the central atom. Well, let's consider which one is going to give the best combination of formal charges. If we look at the carbon being the central atom, we would see that we end up with a minus charge on the sulfur, a singular formal charge. However, if we put sulfur as the central atom, the best resonance structure is going to have a minus on the carbon, a +2 on the sulfur, and a -2 on the nitrogen in order to fill all of the appropriate octets. That is a lot of formal charges and a lot of electrostatic tension on the molecule. That is going to be a very unpreferred structure, and so the one on the left is going to be a much more accurate representation of what the SCN ion is probably going to look like. So to close up here, I want to go ahead and do a little more practice with assigning formal charges just to make sure we have the hang of it completely. So let's go ahead and look at the cyanide ion, Cn-, which is accurately represented by the Lewis structure shown below, with nitrogen triple bonded to carbon with an overall -1 charge. In this case, nitrogen normally has 5 valence electrons, and in this Lewis structure, it has been assigned 5 valence electrons as well. 2 from the lone pair and 3 from the bonds, right? Each bond counts as 1 electron, and so 5 minus 5 is going to be 0. And so nitrogen will have 0 formal charge. Carbon, on the other hand, normally has 4 as a group 14 element, but in this Lewis structure, it has been assigned 5 electrons, 3 from the bond and 2 from the lone pair, and so 4 minus 5 is going to give us a -1 formal charge overall, which is represented by this negative charge here. And notice the fact that the formal charges add up to the overall -1 charge of the molecule. On the other hand, if we look at the hydronium ion, it carries a positive charge and is represented by the Lewis structure below. Hydrogen almost always has a 0 formal charge due to the nature of how it bonds. It really only ever forms one bond and only ever has 2 electrons. So in this case, we want to focus on the oxygen, which in this case has 5 electrons assigned to it. Oxygen normally carries 6 electrons, so 6 minus the 5 that are present is going to give us an overall +1 formal charge on that oxygen. And again, that adds up to the overall formal charge of the hydronium ion, since charge must be conserved. Finally, let's go ahead and look at the ClO radical, which is a chlorine-oxygen radical. If you want some practice looking at Lewis dot structures of radicals, check out our video on that subject. Now, the chlorine atom in this radical is going to have 4 electrons coming from non-bonding pairs, and 1 electron coming from its bond to oxygen, plus another electron coming from its unbonded electron, the radical electron. That gives chlorine a total of 6 electrons in its valence as per the formal charge calculation, which means it's going to have a +1 charge because chlorine normally has 7, and in this structure it has been assigned 6, so 7 minus 6 is +1. Oxygen, being single bonded, is going to have 7 electrons here in its ascribed valence, but normally only has 6. So 6 minus 7 is going to give oxygen a -1 charge. Notice that the overall charges, +1 and -1, are going to add to 0, since this is an overall non-charged species. And with that, we've actually reached the end of the content for this video. Thank you guys so much for watching, and if you like what you saw, please like and subscribe to the channel. To learn more, check out the rest of the videos on our chemistry playlist, and if you're looking to branch out, look at our other science playlists as well. See you next time!